Hello everyone, and welcome to this, our second installment in the two-part video series on the ideal gas law. In the first video, I went over the actual ideal gas law itself, and we talked about how to manipulate it into the various functions that you see right here to find the various pieces of it. So if you want to see that section, go ahead and check out the first video. Again, this is the second one in which we are going to be looking at some actual problems and applying the ideal gas law. Without any further ado, let's go ahead and dive in. Our first problem says a spray can is used until it is empty except for the propellant gas, which has a pressure of 1,344 torr at 23 degrees Celsius. If the can is thrown into a fire with a temperature of 475 degrees Celsius, what will be the pressure in the hot can? Now, with any type of problem, the best thing to do is always, at the very beginning, before you do anything else, make a list of everything you know. So in this problem, what do we know? Right here, actually, I'm going to highlight so that we can follow along. We have right here, we are given our first pressure. So I'm going to write P1 equals 1,344 torr. Okay, let's keep reading. At 23 degrees Celsius. So this looks like it's our temperature 1. Now we have a problem here, and you've probably already caught it. That's that our temperature was given to us in degrees Celsius. For the ideal gas law, it's a good idea to just get in the habit of converting things from 23 degrees, from degrees Celsius into degrees Kelvin. Now here's the thing, you don't always have to do that. But until you get really comfortable with the ideal gas law and the various functions of it, it's best to just put things into Kelvin, because while sometimes you can get away with leaving it in Celsius, sometimes you can't, and it's best to just not take that chance. So for right now, let's just go ahead and convert things straight into Kelvin. And the way you go from Celsius to Kelvin is to add 273 degrees. So I'm going to write, in parentheses, 23 degrees Celsius plus 273. And when I punch that into my calculator, I get 296 degrees Kelvin. So let's keep reading and see what else we know. If the can is thrown into a fire with a temperature of 475 degrees Celsius, okay, that looks like the third bit of information. So let's write that down. Temperature 2 equals 475 degrees Celsius plus 273. So I'm going to plug that into my calculator. 475 plus 273. I get 748 degrees Kelvin. Okay, what will be the pressure in the hot can? So it looks like that's everything that we know. Let's go ahead and think what version of the equation might work here. So the first thing that you do when you're using the ideal gas law is you set two versions of the ideal gas law equal to each other. So we have PV equals nRT, and then I'm going to put a different color right here, is equal to P2V2 equals N2R T2. That's essentially what we're doing when we use the ideal gas law, is we're setting two sides equal to each other. And then within each side, there's a version of the ideal gas law. So what are we looking for exactly? Well, we have P1, and we have T1, and we have T2. Okay, so what don't we have? What we don't have is P2. So how can we relate this to each other? Well, we know that volume is being held constant. We know that number of moles is being held constant. And since we're not having to equate everything to each other, we can also go ahead and get rid of the ideal gas constant. So how can we relate pressure to volume, pressure to temperature? We divide it across. So what we can do is divide by temperature, divide by temperature. Temperatures cancel out. Divide by temperature, divide by temperature. Temperatures cancel out. Now, I tried to use different colors there. Hopefully you can follow what's going on. But really what this all boils down to is we are going to have P2 over P1 equals T2 over T1. So in order to isolate P2 on one side, all we have to do is we have to multiply both sides by P1. And that gives us P2 equals P1 T2 all over T1. Now that we have an equation put together for this problem, we can actually plug in values. And that will give us P2 equals P1, which is 1,344 torr, times T2, which, as we discovered up top, was 748 Kelvin, and divide that entire thing by T1, which was 296 Kelvin. And all I have to do is plug all that into a calculator. So 1,344 times 748 divided by 296, that gives us 3,396 torr, because Kelvin cancels out, right? Kelvin, the only unit that we're left with is torr. So that is our answer, 3,396 torr. Moving on to our next problem. We have a balloon inflated with 3 breaths of air has a volume of 1.7 liters. At the same temperature and pressure, what is the volume of the balloon if 5 more same-size breaths are added to the balloon? Well, again, let's go ahead and just write out everything that we know. We know that the volume of 3 breaths is 1.7 liters. And that is at a given temperature and pressure. Now, it says right here that at the same temperature and pressure. So that means that temperature and pressure are being held constant. What is the volume of the balloon if 5 more same-size breaths are added to the balloon? So we know that temperature and pressure are being held constant. So really all that we have to worry about here is the liters. And some of you may look at this and just it jumps right out, oh, we need to divide 1.7 by 3 because there's 3 breaths. But if you're a little bit confused, the best way to get to the bottom of any problem is to use the stoichiometry and conversion factors. So we can get to the end of this problem by using conversion factors. We can say that in one breath, times that by, we have breath here, right? You can think of this entire thing as being over 1. So one breath times, actually, let me go ahead and put the times down here so it's a little bit more clear. One breath times 3 breaths on bottom is equal to 1.7 liters. So do you see what I've done here? Now, using conversion factors, breath will cancel out. And then we go times, and what's it asking for? Let's see. If 5 more same-size breaths are added to the balloon, and it already had 3 breaths. So that's a grand total of 8 breaths, right? 5 plus 3. So times that by 8 breaths, and put that over 1. By doing that, breaths cancels out again. And if you follow the units across, the only unit that we have left is liters. So whatever answer we get right here is going to be our liters. So to follow the conversion factors across, 1 times 1.17 divided by 3 times 8, that gives us 4.53 liters. And that is the answer to our question. So let's go ahead and move on to the next problem. Iodine, I2, is a solid at room temperature, but sublimes or converts from a solid into a gas when warmed. What is the temperature in a 73.3 milliliter bulb that contains 0.292 grams of I2 vapor at a pressure of 0.462 atmospheres? With this problem, probably one of the most important things that you should realize right out of the gate is that there's information in this problem that we don't need for this problem. If we're going to treat this as an ideal gas problem, the fact that it tells us at the beginning iodine is a solid at room temperature but sublimes or converts from a solid into a gas when warmed, that's irrelevant information right here unless you don't know that iodine turns into a gas at some point. But there are things here that should cue you off to that. So for example, it's asking specifically about I2 vapor. So this is not a problem about phase change or anything like that. So that whole first part of the problem, you can disregard it for the purposes of this problem. And I put this down as an example because when you're taking professional tests like the DAT or the MCAT or whatever you have, or even if you're just studying for a high school chemistry test, a lot of the time questions will put information in that you don't need to try to trick you. So be on the lookout for that, and just make sure that when you're looking at problems, you can sort through the information that you do need and the information that you don't need. For this problem, it looks like we're looking for the vapor. No, we are looking for the temperature because it says right here, what is the temperature? So here's our ideal gas law, PV equals nRT. And as we did in the first video, we know that by rearranging this, we can get T equals PV over NR. And again, if you're not sure how to do that, go ahead and watch the first video in this series where I show you how to manipulate the ideal gas law. So let's go ahead and plug in the bits of information that we have. Temperature is equal to pressure. We have pressure, let's see right here, 0.462 atmospheres. So 0.462 atmospheres times volume. Volume is 0.0733 liters. And by the way, if you're not sure how I got that, look over here. That is our volume, and we know that because we can go 73.3 milliliters times 1,000 milliliters in 1 liter equals 0.0733. So just in case you're not sure how I got there. And then down on the bottom, we need our number of moles. Now, they don't directly give us our number of moles, but we have right here number of grams. And remember, number of moles is equal to grams over molar mass. So in this case, we have 0.292 grams. And the molar mass of iodine vapor, you get that off the periodic table. And keep in mind that you need to use 2 equivalents of iodine because it is I2. And so when you do that conversion, what you should get is 253.8 grams per mole. And that'll be more or less depending upon what version of the periodic table that you use. But I got that we have 0.00115 moles. And then go ahead and plug in the ideal gas constant. And remember, since we're using atmospheres, the version of the ideal gas constant that you're going to use in this case is 0.0821. But remember, that may be a different version of the ideal gas constant dependent upon what units you're using. But again, in this problem, we're using atmospheres, so we're going to use 0.0821. And when you do this math, just go ahead and plug it into your calculator. I got 358.68 Kelvin. So that is your answer right here. Moving on, we have our next problem. Calculate the density of Freon 12, CF2Cl2, at 30 degrees Celsius and 0.954 atmospheres. For this problem, we need the version of our ideal gas law that includes density. So remember, I want to use black. Let me just go ahead and change the color. Okay, density is equal to pressure PM over RT. Now, if you're not sure how I got this version of the ideal gas law, go ahead and watch the first video in this series where we worked on the conversions. But this is the version that we're going to use right here. Density equals molar mass times pressure over R times T. So that's what we have written right here. First thing that we need to do is we need to find the number of moles that, or the molar mass, excuse me, we need to find the molar mass of CF2Cl2. And in order to do that, just pull up a version of the periodic table, and we're going to plug in the molar mass of those various elements and add them all together to see what we have. So we have CF2Cl2. Carbon is 12.01 grams per mole. Let's see, we have fluorine, so we have 2 times 18.99 grams per mole. And we have 2 chlorine, so 2 times 35.45 grams per mole. And if you add this all up, you're going to get around, again, dependent upon what version of the periodic table that you're using, around 120.89 grams per mole. And now we just need to go ahead and plug in the rest of our information. So we have D equals pressure. Pressure, they gave us 0.954 atmospheres. Multiply that by the molar mass, so times 120.89. And that is all over, let's see, the ideal gas constant. We're using atmospheres, so in this case, again, 0.0821 times the temperature. Now, again, remember, you cannot just plug in Celsius. There are versions of certain equations where you can use Celsius. Those instances are when it's simply a ratio. However, since we are using the ideal gas constant, in this case, 0.0821, degrees Kelvin is a part of that ideal gas constant. Because remember, the ideal gas constant has units. And so in this case, Celsius, or the degrees in the temperature, is not simply a ratio. It is an integral part of the units that we're using. So you cannot use Celsius in this scenario. So don't forget to add 273 degrees to the 30 degree value that we were given. So you add that together, and what we actually have is 303 degrees Kelvin. And when you do the math on this, you should get around 4.64 grams per liter. And remember, grams per liter is our units of density. So that is our final answer. Moving on, we have another problem here. A cylinder of O2 gas used in breathing by patients with emphysema has a value of 3 liters at a pressure of 10 atmospheres. If the temperature of the cylinder is 28 degrees Celsius, what mass of oxygen is in the cylinder? Okay, this is a scenario where we're going to have to manipulate the ideal gas law just a little bit so that we can get it in a form that we can use. We know that the regular ideal gas law is PV equals nRT, but this is asking for mass of oxygen. So the version of the ideal gas law that we're going to use is this one right here. Now, all we need to do is rearrange this in order to get grams. So we are going to multiply both sides by molar mass, and that gives us and then we go ahead and divide both sides by RT, and this gives us grams equals mmPV over RT. And now we have a version of the ideal gas law that we can actually use. So let's go ahead and plug in these values. We have 10 atmospheres times 3 liters times 32 grams per mole, because remember, O2 is that's a horrible looking one, 16 grams per mole. Again, dependent upon the version of the periodic table that you're using. But O2 gas has 2 oxygens per molecule. So the molar mass is 32, not 16. Don't forget that step. And then that's all over the ideal gas constant. Again, we are using atmospheres. So the version we're going to use is 0.0821. Times that by the degrees. And again, remember, you cannot use the degrees Celsius. You have to add 273 degrees to get your Celsius into Kelvin. So this is the final version that we're going to use. And if you plug all of that into your calculator, you should get somewhere in the neighborhood of 38.8 grams. So that is our final answer for this problem. Let's go ahead and move on to the next problem. What is the molar mass of a gas if 0.281 grams of the gas occupies a volume of 125 milliliters at a temperature 126 degrees Celsius and a pressure of 777 torr? Okay, so for this problem, pretty straightforward. We're just trying to find the molar mass of the gas. So again, we're going to have to manipulate our ideal gas law a little bit. We have PV equals nRT, but obviously we need molar mass. So the version that we're going to have to use is PV equals grams over molar mass RT. Just multiply both sides like we did in the previous problems. We get molar mass times PV equals RT. Divide both sides by PV. Oh, and I almost forgot to put grams right here. Whoops. Okay, and that gives us the version of the ideal gas law that we're going to use, which is molar mass equals RTG over PV. Now, another really important thing to keep in mind here, as I've highlighted right here, is that this problem is giving us our pressure and torr. Now, there's a couple different ways that we can approach this. You can know that the ideal gas constant is 62.36. 62.36. See, I don't use that very often. You can know that the ideal gas constant is 62.36 if you're using torr, or we can just go ahead and convert torr into atmospheres. Now, most chemistry professors are not going to make you memorize this version of the ideal gas constant. So I would just make sure that I was comfortable converting torr into atmospheres. I think that that's the easiest way to approach this problem. So 777 torr times there is 1 atmosphere in 760 torr. So if we hurry up and throw that into our calculator, 777 divided by 760, really what we have is 1.02 atmospheres. And again, I think that's the easiest way for most people to approach this problem, but you could use the other ideal gas constant if you prefer. It's up to you. But let's go ahead and throw in our values. We have that the molar mass is equal to 0.0821 times, and again, don't get thrown off by the fact that this is giving us the temperature in Celsius. It's 126 degrees Celsius plus 273 to get us to the temperature in Kelvin. So it's really 399. And then multiply that again by the grams, which is 0.281. No conversion required there. And then we put all of that over our atmospheres. So 1.02 atmospheres. Again, make sure that you match it. We're using atmospheres here because we're using the 0.0821 gas constant. and multiply that by the volume. Now, one more conversion is going to be required here. We have 125 milliliters. Now, don't forget that we need to turn this into liters. So the easiest way is just to remember that there are 1,000 milliliters in a liter. So just go ahead and move the decimal 3 places to the left. And that will give us 0.125 liters. Now let's plug all of this into our calculator and see what we have. When I plugged that into my calculator, I got about 72.2. And again, that number could be a little bit different for you dependent upon what version of the ideal gas law you use, but it's going to be pretty close to the same. It's just going to be give or take a few decimals, right? But that's about what I got, is 72.05 grams per mole. And that is the answer to our problem right there. So let's go ahead and move on to the next problem. A mixture of 0.2 grams of H2, 1 gram of N2, and 0.82 grams of argon is stored in a closed container at standard temperature and pressure. Find the volume of the container, assuming that the gases exhibit ideal gas behavior. The key to this problem is just understanding the principle of partial pressures and how those partial pressures can relate to the total volume of the container. So the first thing to do, remember, when it comes to chemistry, it's really hard to compare grams of a substance to grams of another substance because the molecules are different sizes. Really, when it comes down to it, the best thing to do anytime you're given a problem that has grams of different substances, go ahead and convert all of those into moles, because moles are the only real thing that you can rely on to compare two substances across the board. So it looks like we have 3 substances here. Let's just start from the beginning. We have 0.2 grams of H2. Now, in order to get this to moles, we need the molar mass of the substance. And keep in mind that when you look at your periodic table, whatever the value is for hydrogen, usually it's around 1. Whatever the value that you're given for hydrogen, you have to multiply that by 2 because hydrogen is a dye substance, right? There's 2 of it, 2 molecules of hydrogen in a molecule. So we have 0.2 grams of H2, and remember that moles is equal to your grams divided by your molar mass. So when I multiply by 2, I get 2.016 is my molar mass, so that's grams per mole, right? And that gives me about 0.0992 moles. Now, another thing to commit to memory, if you take the DAT or the MCAT, this will help you so much. This is an enormous time saver and life saver too, I guess. Just remember that when you're trying to convert moles into liters, this conversion factor right here, in 1 mole, there are 22.4 liters. That always holds true for any given ideal gas. So I'm telling you, if you remember this conversion factor right here, this is such a time saver. If you know this conversion factor, you don't have to go through the entire density equation to compare moles to liters. So here we go, 0.0992 moles times 22.4 liters per mole. And that gives us that we have about 2.22 liters of H2. So see how I've done this here? I've gone from grams, which is what we were originally given, of H2, and I've taken that to liters of H2. So let's go ahead and do this same thing for our other substances. Let's see, moles of N2. We have 1 gram of N2. Put that over 28.01 grams per mole. Again, don't forget when you look at your periodic table to multiply your molar mass of nitrogen by 2 because this is a N2 molecule, not an N molecule. And that will give us about 0.0806. Oh no, excuse me, I'm jumping ahead of myself here. That will give us about 0.036 moles. And we times that by this wonderful conversion factor again. Moles cancel out, and we are left with 0.8 0.806 liters of N2. Now we'll do this lastly for argon. Number of moles of argon is equal to our grams, and we have 0.820 grams. Now this time we don't have to multiply by 2 because argon is a noble gas, and so it's not going to come bundled in groups of 2. In any given molecule of argon, you just have argon. So divide that by 39.95 grams per mole, and that will give us about 0.02 moles. And we multiply that by 22.4 liters over 1 mole, and that will give us about 0.46 liters. Now, this is what I was talking about when I said partial pressures. This same thing applies to your liters. Any given pressure or any given volume, there's going to be a mix of everything inside. And because gases are so unrestricted, right? They're moving around, they're bouncing into each other, they're not packed together tightly. You just take the individual pieces or the partial parts of the whole and add it together, and that will give you whatever the whole is. So all you have to do is just add all of these liters together. So we have 2.22 plus 0.806 plus 0.46, and that gives us about 3.49 liters. And that is the final answer to this question. Let's just do one more problem here. An unknown gas has a density of 1.79 grams per liter at 273 degrees Kelvin and 1 atmosphere. Identify the gas. So there's 2 ways that we could approach this problem. There's the conventional way where we could go ahead and do the ideal gas law. And remember, we've drilled this home by now. You probably realize that an equivalent version of this is this right here. Now, we could go ahead and use this equation to identify the gas. And the way that we would do that is we would solve for molar mass. And then whatever molar mass ends up being, you can compare that with the periodic table and see what you have. But there's a shortcut to this problem. And it's kind of like what I showed you up here. And this is a beautiful shortcut, especially if you're taking a professional test. This will save you so much time. All you have to do is realize that there are 22.4 liters in 1 mole of any given ideal gas. Doesn't matter what it is. So in this case, a shortcut would be to realize that our density is 1.79, and that is grams per liter, okay? And if we use this idea right here as a conversion factor, what we could do is we could say, okay, well, we know that there are 22.4 liters in 1 mole of a substance. And if we do the math on this, 1.79 times 22.4, that gives us 40.01. And we put that over 1. And then let's go ahead and use our conversions and see what units we have here. Well, we know that liters canceled out. And so on the top, the only thing that came across was grams. And on the bottom, the only thing that came across was moles. Okay. And if you look at this, you think, okay, well, my units are now grams per mole. Hey, that's the same units as molar mass. So if we look at the periodic table to see, okay, what substance has around 40.01 grams per mole? Well, it's argon. So we know that the final answer to this problem is argon. And that is it for this video. So thanks for watching. If you liked the content in this video, go ahead and give this video a like and subscribe to our channel. That will help us continue to make more videos. And as always, if you have any problems that you're stuck on, go ahead and shoot us a message or leave us a comment down below. And if it gets enough likes, we'll make a video about it. Thanks, and we will see you next time.